List of the teams.
Hi.
No problem.
I'm with her.
Oh, you can share if you don't mind.
Thank you.
Oh, look, there's chatting.
That goes for this column, and the output of this node. That'll be the dot product of the voltages and your conductances, the dot chip. And dot products are very common in machine learning, right? If you look at ChatGPT, every time you run a ChatGPT query, you're doing a 175 billion dimension dot product, right? So that means you have 175 billion values in one vector, 175 billion in another vector, multiplying the pairs out. Very expensive. Numbers are expensive for that. It's very formal in-memory computation. There is no fetching between different registers. All the computation is done directly on the registers and not all files. So you don't have to constantly supply power to So what we did is we collected data from the lab. We're going to do a little demonstration.
Yeah. Feel free to interactive here.
Write a number, try to make it thick. Write any number from
Write
0
a digit, a single digit. Yeah.
You get the whiteboard with the marker, right?
the computer.
It doesn't matter. We're going to see it in the whiteboard. No, it's not that good yet. It can't predict lines.
So what's happening here is we've gotten this model, and this is pretty common. This is a pretty good benchmark for machine learning. This model that's trained to recognize these digits. But what's happening for the prediction phase is, see, he's capturing the picture. It takes the picture and turns it into a digital image for it to process. What's happening here for the prediction phase is instead of doing the multiplication traditionally, we're simulating our little voltages being applied and our current getting read. So that's all done through simulation. So yeah, so the training is already there. And this is kind of common for these types of devices. You want to do the prediction on them. So we're able to take the picture that you did and do all the multiplication for the prediction on the devices. Let's see. We should try to use that. Oh, that works. So let's see what it predicts. It's an 8!
Hey, there we are.
So, what this is doing is we collect the data from the lab showing how the conductance of these memristive changes as we supply positive and negative pulses, right? And what we did is we used this data to make a function that takes the weights of our machine learning model and encodes them as conductances on our simulated memristivs, right? It tunes the memristivs throughout this plot to have conductances as close to the weights we want as possible. And we have a little demonstration. We took an image of our mentor doctor, I can say this data. We took the pixels and the grayscale downloads, encoded them as conductances on this plot, then decoded those conductances, and replotted the image. You can see it's mostly the same image. So in one dimension, this works very well. Now what we're doing in this little demonstration is trained a model which can classify digits, right? This is a common machine learning problem called MNIST, where in the 1960s, the US government collected tens of thousands of handwritten digits from elementary schools. And they assembled a data set where the goal is to make a function that takes a 28 by 28 pixel image and classifies it as one of the pair digits. This is a very common benchmark for machine learning models. Right, and we trained the model on these memristivs. This animation shows how, as it's training, how did the weights, how did the conductances on the memristivs change. Right? Red pixels mean it's more likely to be that digit. Blue pixels mean it's less likely to be that digit. So you can see the weights for the digit 2 look like 2. The weights for the digit 0 look like 0. The rest of them look a little more abstract, but That's what our model says. And so we implement these our members use performance computations. We can compare them to digital methods. On the traditional memories data set, the digital methods can get you a 94% accuracy with logistic regression. You convert that to memrisers, it drops to a 92% accuracy. The reason is we don't have perfect precision when encoding weights as conductances. There are only so many points on this plot because memrisers are very sensitive to pulses, right? Just supply voltages instantaneously. Its conductance changes wildly. So this is already very idealized. But our simulations show that as you increase the number of dimensions, right, the number of weights on the model, or the number of members, accuracy doesn't increase, right? It's always roughly around 2%. And as a consequence of that, in theory, you can implement these on as large a scale as you want. Now, obviously, we're still nowhere near to ChatGPT 175 billion, but this is still already much faster than any digital method because this is a 784 pixel image, right? So you would only need 784 membrisers to do this calculation, right? You compare that to a digital method, you could need probably 100,000 transistors to do this sort of calculation, right? Depending on the precision you use. So it's far less components. If you think about power consumption, it's not volatile memory, so once you tune the conductances to be as close to the weights as you want, that you've already done all the tuning, you're just supplying small voltages and then feeding that to an ADC, an analog to digital converter, to get your prediction whenever you get the prediction stage. So this is far more energy efficient than any digital method. And our simulations show it can be scaled up as much as we can talk about hardware.
Any questions?
No, I'm a non-science person, so I'm very very hard and I should interact with them. So what are the real world?
It's pretty good for PhD students especially because they're just kind of like crank out papers and get their research done. It's kind of this antiquated technology and all these like old programming languages from the 80s is a pain. So we're trying a very like modern Arduino-based system for hardware and we can apply it to small arrays of membrisers. And we're doing a simulation to show like, hey, once these products get out of the research phase and they're not very, we tinker with them a bit right now and they can break. Once they come out of the research phase, we can say, oh, do some big simulation. So kind of have a hardware and software stack.
Oh, that's cool because people always have
Yeah, the size of your watch.
yeah, that's my watch actually.
Any other questions? What non-volatile memory is?
Over my head.
It's okay. Thank you. Maybe that's your family walker.
Yeah, it's from the parents.
Oh, hi. How are you?
Oh.
Take a picture, so bring the code, I pull this up, All right, so it encodes it as a 28 by 28 pixel image. It sort of pads the edges because we typically have problems with shadows.
One is I thought you only wanted to see your kid, so.
Do you want to write a different digit because it just classified an 8?
Okay.
So you kind of let's see even do it. Okay, you did it.
Hey, there we are.
All right. Yeah, let's get a new digit.
Walker, our system's a little better than we
no.
thought.
Yeah, maybe it always classifies 8.
Okay, let's hope this isn't too much shadows
Okay,
and stuff on it.
another numbers. Okay, so did it. Awesome.
It got the
You
8.
got it.
got the
Okay. All right, I'm gonna do tricky here. Let's see.
Oh,
if
no.
Oh, whoa.
Okay.
4. All right.
Do it.
Yeah, we'll see. It's not, it tends to mix up 1s and 4s. From what
I like that was the first one that we did.
Let's see.
A little thicker. Maybe it. Hey.
Oh, okay.
Wait. Wait. Did it classify as an 8 or no? Oh no. It's the next one.
Not great. 4 was its 4th choice.
It's 1/2 out of
Just
10.
a 9?
Yeah.
Fours are tricky because a lot of people write them differently.
Yeah, 9 was its 2nd choice. That makes
Okay, I
sense,
can
right?
see a 9 with that for sure.
Yeah. I don't know how it predicted 8.
Wait, maybe the circle
I
on
didn't
top?
say, but it says probability of being. Oh.
Yeah, these probabilities don't add up to that's part of
I feel like they for sure would.
Yeah.
I like that it shows your face and you're holding up a
Hello, I'm Garrett. I'm senior in electrical engineering for group 48.
can only be like a.
What question do you want to ask me? Sorry.
Hi, my name is Jaffar Al Shamari. I am on Group 48. I'm a senior EE, and my main kind of interest in EE is digital electronics, and this kind of is a nice gap between analog and digital. And I'll be graduating very soon, hopefully, and going to work. So that's all. Thank you.
Hi, my name is Samarth Singh. I'm an electrical engineer, senior next year, but I'm going to 4+1, so next year will be my graduate year. Hopefully, out of this major, I hope to work in like a digital circuit design, or maybe even if this goes further, I'm doing more research on this next semester. If this goes out, maybe do my own thing regarding this.
Very good.
Yeah.
All right.
Hi, my name is Raj Vyas. I'm a senior in electrical engineering. I'm Walker's teammate. He's quite brilliant, so it made my job a lot easier, but I'm also going to 4+1, and I'm going to computer engineering for electrical engineers, basically computer architecture route. The same route as Garrett and Samarth, so I'll be seeing a lot of them, which is, I think, pretty good. But yeah, I'm excited to be part of this team, and it's been a really fun ride.
Hello, my name is Walker Kroubalkian. I'm a senior electrical engineer at Arizona State University, and I am the software lead on Team 48 Analog AI Accelerator for machine learning applications.
So basically, the image would start. Let's start with an image. I think that helps a little bit better. So basically, our mentor, he works in a lab, ISE lab, and this is the machine they use right now to work with the memristors. As you can kind of see, it's pretty large. Only a couple of people you can use it. People can use it, like PhD or like master's students. It's very hard to use. Our goal in this project is to make something like transfer all the capabilities of this into the simple machine. So this hardware does two things. This section does a write function. Basically what it does is basically pulses positive and negative voltages to charge the memristors. In this case, we put up a resistor for testing, but memristors and resistors are kind of the same thing. And this circuitry, what this does is it reads the current that comes out of it at the end. It's basically an op-amp in a transimpedance amplifier circuit, and basically what it does is it takes the current that it gets out of this memristor, converts into a voltage, and using our ADCs we read it, and through that we kind of learn what the conductance on that thing is. So that is the basic rundown of that.
Hey, do you have Walker? Denise, do you know where Walker is? Have you heard from Jaffar?
I just want to check out.
Is that the list of projects? Can I see one?
Honestly, I don't think how many projects there are. Like, now I have
So you can hear the hidden credits.
there's a parent stuff, I think.
Yeah. What a great discovery. So this is an aerial view in the ASU Fitness Center. And Walker's describing what's going on here to another group here. It's the Memristive project. A lot of people here. A lot of very cool projects. Even refreshments are served.
So you're up there? Garrett. That's exactly what I have to
Should I go back? I don't know if
Pardon?
nobody's interviewing them, so I got to be around our team.
Sure, sure. No worries.
But, it was good to see you guys.
So what time?
liked your class. That's the main reason why I ended up going to signal processing. Yeah.